Okay, let's get started. It's 12:35. I'd like to welcome you to the second SEMCME Research Workshop. I'd also like to welcome the people that are listening to this, watching this presentation remotely. Welcome to you as well. My name is Karen Hageland. I'm a medical researcher at Ascension St. John Hospital. I'm also proud to serve as chair of the SEMCME Research Committee. So on behalf of the entire committee, I'd like to welcome you to the second research workshop. Let me ask you, how many of you were here for the first research workshop? Okay, so I'd say maybe about half of you. So at the first one, we talked about research design. Today's focus is more on statistical testing. Let me just give you a rundown of what we're going to be covering today. So the first talk is by myself, and I'm going to be giving you an introduction to statistics. And then at 1 o'clock, we're going to have Dave Sangstock, lead at Interactive Journal Club. And we're going to, we've always had, on your evaluations, we've had information from you that you would like to have more interaction. And so we built this in today's program to have you break up into groups. So you should have a number that was given to you, and we're going to divide you up into 7 groups. So we'll give you more instruction when we get to that point. But we're going to have moderators from the research committee come in and break up into groups, and we're going to discuss in detail a research article. And so I think that exercise, you'll find it very beneficial. Right after that, I'm going to go more into details about statistical testing. And then our last speaker is from Merck, who's going to be speaking about relative risk ratios and odds ratios and intention to treat and all those good things. So I think please plan to stay for the entire program, because if you leave early, you'll be missing out. Especially our last speaker is, I reviewed her slides earlier this week, and she's giving some very helpful information. So I would encourage you to please stay for the entire day. Just some housekeeping details. Let me just tell you a little bit about SEMCME. SEMCME is the largest community-based medical education consortium in the Midwest. Its primary mission is to stimulate the delivery of quality care through excellence in graduate medical education and faculty development. You should have signed in at the desk and received your badge and some materials, some handouts. Also, later on, we'll be passing out a handout that has a QR code that's going to have a link to a SurveyMonkey survey for an evaluation of today's session. So we keep that information. We hold it very, we hold it with great regard, and it helps us in planning next year's workshop. So please take the time to fill out the evaluation. In fact, we're going to allow at the end of the program 10 minutes to do that today. And we also, we have a lot of the experts from the research committee that are coming in. So if you have a specific question about your own research project, feel free at that time to talk to somebody about that if you would like some guidance. How many of you at this point have actually started a research project? Okay, so just a couple. So most of you are probably at the point where you're just kind of worried about it and wondering what you're going to be doing and how you're going to design and how you're going to come up with a topic and a hypothesis test. So, so that's what we have this workshop geared for, the one that we had last month and today's as well. So I hope that we put a lot of effort into these workshops, so I hope you find them helpful. Okay, I think that's all I wanted to say for just the introduction. So let me get now into my talk, the first talk of today's agenda, which is Research Designs and Potential Interpretation of Data, Introduction to Statistics. And so at Ascension St. John, I've been there for, I don't know now, 27 years, I guess it is. And I help residents like yourself throughout the entire process of research, so every step of the way. So I'm going to give you kind of a synopsis of what I know through all these years and how to help residents. So what I like to do is say, let's take your research project step by step, because it can be overwhelming, the idea that you have to do a research project. So I talked about this last time, but I just want to go through it again today. And of course, today we're going to focus more on statistics. But your first step is to identify a topic. And, there's no right or wrong way of doing that, but just make sure it's something that you're interested in, because it's going to be a long process to do your study. You're going to have some roadblocks. You'll get frustrated. But if it's really a topic that you're interested in, that'll help carry you through the process. Also conduct a thorough literature review, have the librarians at your institution help you. Define your variables of interest, and when we have our interactive session today, we're actually going to be defining from the article that we have the independent variable, the dependent variable. So hopefully you get used to thinking in those terms. You have to come up with a testable hypothesis, and of course I know you've heard about this for a long time throughout your education, but believe it or not, it's not always easy to come up with a testable hypothesis. Design a study using the best design you can with the time that you have and the question that you're asking. Come up with power analysis, so how many subjects you'll need for your study. Write your protocol. Design data collection tools so that when you go out to collect your data, it's very streamlined. You know exactly what you're collecting. Go through various committees. So all of you will need Institutional Review Board review or IRB review. Even if you think your study is exempt, you can't decide that on your own. You have to have IRB review and have them tell you that it's exempt and get a letter stating that. So you always want to make sure that you've had IRB review before you collect any data. And hopefully you'll get your approval letter. A lot of your studies will be expedited, and so you won't need to go through full board review. So hopefully you'll get that process, go through that quickly and get your approval and be on your way. Then you get to collect your data once you have approval. So you've got to make sure you have time for that in your schedule, that it's feasible, that if you're having anybody else help you, that you've got them on board. Then you get to set up a spreadsheet to enter your data. Most people use Microsoft Excel for this. It's always good to have your statistician help you set this up because you just want to make sure that you're putting in the right information in the right format so that there's not a problem then when you actually have your statistics run. Just yesterday, I had an OB resident give me a column in Excel of gestational age, and I looked at the gestational age in weeks, and it was funny because there was nothing like 39.8 or 39.9, because he was putting in 39.4, let's say, it's 39 weeks and 4 days. Well, it's not, 4 divided by 7 is the fraction of the week, so 39.4 isn't really the real number of gestational age, if you understand what I'm saying. So he had to go through and change all of those, so it was really on the scale of a week. So those are the kinds of things that it helps to have somebody look over your spreadsheet before you've entered thousands of pieces of information and then have to go back and redo it. So entering your data. And then statistical analysis. I've got this in bold because that's what I'm going to talk to you about today. And this is actually my favorite part of my job. I really actually love getting a set of data and actually running the numbers because I think this is exciting because this is the point where you get to answer your research question. You get to see if you have support for your experimental hypothesis. So you've done all this work and now you're finally going to get an answer. You're going to find out whether one treatment is better than another, for example. Then you want to graph your data, and that always is very helpful because this is going to be how you present your data when you make your slides, your poster presentations. And then, of course, you want to write up your study. You already have the first half written from your protocol, so now you're going to add your results in your discussion. And so those are the steps. And so I think it helps you just to break it down like this and not have such an overwhelming task. So those of you who haven't started, you know what the first step is now. So let me jump to the statistics step. Are you confused by statistics? Well, we know that there's a lot of statistical tests out there. You'll see it in today's paper that we're reviewing. They actually run some kind of complex methods. I'm going to make things very simple for you because I've gone through a lot of resident projects. I know what the main statistical tests are. I know what's used 95% of the time, and that's what I'm going to talk to you about today. And you probably had some of this in medical school, but it was probably brief. You probably haven't looked at it since you had maybe, took your MCAT or went through this in medical school. So most residents come to me and say, I kind of remember what a chi-square is, but I kind of don't because I really haven't used that. So I'm going to refresh your memory today and talk about the major tests and not give you anything beyond that. So your goal here is to understand why a particular statistical test was used for your research project. So you're going to have your statistician run your statistics. Hopefully that person will sit with you and go through your analysis test by test and explain to you why a particular test was used and what the results were in your case. And then you need to interpret these results because you're going to be presenting them. And it also helps to understand and evaluate the medical literature. So if you understand something about basic statistics, it'll make it a lot easier to understand and evaluate the medical. Not to perform your own calculations. There are statistical packages available online. You can get into those pretty easily. But what I always tell residents is it's kind of like garbage in, garbage out. And that if you put in garbage, you're going to get out garbage, and it may look like you've actually got some analysis that looks like on paper like it makes sense, but if you weren't running the right test, then it really doesn't make sense. And so I hope that you don't go through this alone. I hope that you have somebody at your hospital that can help you with this. So there was a study that was done, it's a long time ago now, in 1983. It was published in the New England Journal of Medicine. And what they did is they looked at the level of statistical expertise necessary to read the literature. And I think statistics have gotten a little bit more complicated since then, but you know, I think this also is pretty relevant to today. So they looked at all the articles that were published in the New England Journal of Medicine over a particular time, and they kind of put the statistics into categories. And 58% of the statistics that were reported were just descriptive statistics. Okay, so percents and means and standard deviations, very simple things, just describing the population. Usually, you know, your table, table 1 in the results in a paper will be, you know, the basic demographic breakdown of your patients, of your subjects. If you added something called t-tests, which I'll go over today, then you gain up to 67%. And if you add contingency tables, epidemiologic statistics, Pearson's correlation, simple linear regression, analysis of variance or ANOVA, all things I'll cover this afternoon, then you're jumped up to 84%. Okay, so that's a pretty, you know, it's a lion's share of the pot here of what you can understand. So you don't need to be a statistical expert to really grasp most of the literature, even in the New England Journal of Medicine. Okay. So before you choose a statistical test, you have to figure out your variable type. And so that's my first step. When I see your data and I get an Excel file, I try to figure out what the scale of measurement is. So I'm going to spend a little bit of time on this because this is your first way of figuring out what statistical test you use. So you have to decide whether your scale is qualitative or quantitative. And then you have to figure out what your goal is. Is it to compare groups? And if so, how many? Do you have 2 groups? Do you have 3 or more groups? That's going to make a difference as to what statistical test you use. And are you measuring the relationship or association between variables? Okay, then you'll be using some other tests. So the 4 scales of measurement, so luckily there's only 4, and you can actually say there's really only 2 because you lump the first 2 together and the last 2 together. So these are the scales. So the lowest one, the totem pole, is the nominal scale. Then a step up is ordinal. A step up from that is interval. And a step up from that is ratio. So nominal, I'm going to go through these in turn. All of you will have data that are measured on a nominal scale. The simplest scale, variables have no numerical value, but they have categories. So you simply count up the number in each category, calculate a percent. So in a study in Table 1, you might read that there's 48% males and 52% females in the study. So that's an example, a gender of a nominal scale variable. Race is another one. So you'll probably collect race in your study. You may collect marital status. You might record as an outcome whether or not a tumor recurred. And something often used in medicine, final measurement is whether somebody's alive or dead for their outcome. So these are all nominal scales. So in your Excel spreadsheet, you may say alive is 1 and dead is 0, or vice versa. But that doesn't, you know, that doesn't hold any mathematical weight. You can't take an average of that. You're just going to record how many zeros you have and how many ones you have. But you're all going to have data measured on this simple scale. Then to move up is an ordinal scale. And here you have underlying order to the category, so you can rank them from highest to lowest. And the intervals between them may not be equal. So if you think in terms of a race, somebody comes in first place, somebody comes in second place, somebody comes in third place. So if you record how many minutes that is, maybe the first person, comes in 20 minutes, and the second one in 22 minutes, and the third one is 3 minutes behind that person, maybe they come in 25 minutes. So the intervals aren't equal, but you can assign them first, second, and third place. So in medicine, you have things like cancer stages, APGAR scores. You might be tempted to take a mean of an APGAR score, but technically it is categories that you're counting to come up with the APGAR score, so it's really not a ratio scale variable. Pain ratings, and anything measured on what's called a Likert scale. And you've all seen Likert scales where you have strongly disagree to strongly agree, maybe a 5-point scale. That's a Likert scale. So all of those are measured on the ordinal scale. So you might very well have ordinal data in your analysis as well. But the nominal and ordinal will be lumped together in terms of the analysis that you do. And then moving up from that is an interval scale. This is quantitative data. You can add and subtract the values, but you cannot multiply and divide because you don't have a true 0 point. And you don't need to worry about this scale because the only example that anybody ever gives for this is a temperature. And so that would be an interval scale, and that would be the only example for this. And then ratio scale, you're going to have ratio scale data in your study. These are real numbers. True 0, you can do all math on it, add, subtract, multiply, and divide, and you have age, body weight, blood pressure, length of stay, OR time. Okay, so now with this type of data, you can actually do the highest level statistics. So the first two, nominal and ordinal, lead to what we call non-parametric statistics. They don't have as many assumptions that have to be met in order to run the statistics on that type of data. And then you have interval and ratio scale data that lead to parametric statistics, which have more assumptions about the data. And I'll be telling you what those assumptions are a little bit later. Okay, any questions on that? If you have a question at any time, I should have told you, but if you have a question, please raise your hand and I'll be happy to answer it. Any questions? Okay, good. It sounds very basic, but you'd be surprised, I mean, this is the first thing you have to figure out when you're looking at data is what the scale of measurement is, because that's going to lead you to different types of statistics. Okay, so there's actually two branches of statistics. There are descriptive statistics that all of you will be calculating in your study, and there are inferential statistics, which I would say most of you will be using as well. So the descriptive statistics include things like frequencies and percents, measures of the middle, measures of variation, all important information to describe your data. And then, but when it really gets fun though is the inferential statistics, because here you're testing your hypothesis. So here you're running things like chi-squares and t-tests, and you're getting p-values. Let me talk about descriptive statistics first. It's your first step in analyzing data. And your goal is to communicate the results. You're not really trying to generalize beyond your sample. You're simply trying to describe your sample. So this is actually, I cut and paste this in from the statistics package that I use, which is called SPSS. And I'm doing a study where I'm looking at people that are either smokers or non-smokers. And so you see here I have a frequency of smokers of 26. That's how many smokers, and I have 79 non-smokers. And so I have simply counted up the number of smokers and non-smokers and reporting the frequencies there. I'd also like to report the percent. In this case, I have a number of people that are missing. You see missing says 22. So I couldn't either ask them or I couldn't get from the patient charts what their smoking status was. So in this case, I don't want to just report the percent, I'll report the valid percent. I'll throw out those 22 missing. My denominator now will be 105 rather than 127. And so now my smoking percent is 24.8. and my non-smoking is 75.2. So that's what I'll report in my study. Is that clear? Okay, so just simply counting up the number of smokers and reporting the valid percent. So that's something that I'll want to know. I'll want to know what my rate of smoking is in my study, because probably what I'm doing is designing a study to see whether I can have an influence on that. Maybe I can help these smokers quit smoking. I also want to not only describe what's going on in terms of just how many people in the categories, but if I have continuous data, I want to know what the middle point is, or the central tendency point. So I'll calculate a mean or an average. And it's a common measure, but it can be easily influenced by outliers. And the example I always give is, let's say you compare two different groups of people in terms of their salaries. So let's say I go around to this hospital today and I ask the staff what their salary is. And then I take another group and I ask them, maybe I go to one floor and I ask them what their salary is, go to another floor of the hospital and I ask some staff what their salaries are. And then the last person I encounter, I don't know why this person is visiting the hospital today, but maybe I run into Bill Gates. And so I say, hey Bill, what is your salary? And he happens to be on the 5th floor, my second group of people. And so I put his salary in there. So now I calculate an average for my first group and then average for my second group with Bill Gates. Well, I think you can see that that's not quite fair, because the average for the second group is going to be astronomical because I put Bill Gates' salary in there. Okay, so that's the kind of thing where you have to worry about whether a mean is representative of the middle point. So you have to look at the distribution of your data. So you may want to use a median instead. So if I use the median in this example, that's the 50th percentile score. Think of it as a median in a highway that divides the lanes. Okay, so I have half above and half below, and so now Bill Gates, throwing him in the pool doesn't really matter, because I'm going to just report the middle score for each group. So when your data are skewed, are not symmetric, then you want to use a median instead of a mean. And I might want to know what the most frequently occurring score is too. So that would be my mode. And then, of course, I want to know how much variation I have. So if I have that group with Bill Gates, I'm going to have a lot of variability. If I threw him out, I wouldn't have as much variability. So I want to calculate a standard deviation. And sometimes I might even want to calculate a standard error, which will be a smaller number because it's the standard deviation divided by the square root of the number of values. So sometimes if I'm making a graph, for example, I might want to graph the standard error rather than the standard deviation because it's a smaller error bar on a bar graph. But usually in a table, you're going to report the mean plus or minus the standard deviation. Other measures of variation that you could see is the variance, which is a bigger number because it's the square of the standard deviation, or the range, and that's helpful sometimes, just knowing what the largest number is and the smallest value, particularly for age. Maybe you want to say your youngest was 18 and your oldest was 90, and so that would be the range that you're giving. So here are my people in my study. I've got 26 people here, and I record how many cigarettes they smoke. So I got 2 people that smoke 1 cigarette, got 1 person that's smoking 100 cigarettes a day, and so I can see my frequency distribution here. So that's right, I cut that out, I copied and cut that right from SPSS. So that's how your output could look in your study. And then I have some descriptive statistics here. So I have my 26 people, and the mean number of smokers, rather, and the mean number of cigarettes that they smoke is just under a pack a day at 19.62. The median, or 50th percentile score, is 16. The mode, the most popular amount of cigarettes to smoke would be 5 a day. You see my standard deviation is quite large at over 20. I'd say anytime your standard deviation is more than half of your mean, you've got a lot of variability in your study. And of course, my range is 99 because it's my maximum of 100 minus my minimum of 1. Okay, so that's very helpful to know all those statistics. Okay, so that's what I have to say about descriptive statistics. I'm just going to take just a couple more minutes here to talk about confidence intervals, because I know later on we're going to focus just on key values. But it's also important to look at the confidence interval because that shows you the range in which we're reasonably likely to find the true value. So it moves away from just worrying about the p-value, and journal editors are increasingly demanding that you report these. So your p-value is going to tell you, okay, do you have a significant finding or not? Do you have an effect? Did your treatment have any impact? The confidence interval is going to tell you something about the effect size and how much of an impact. So an example here, let's see which one gives more information. So the first sentence is, the difference in 1-year survival rates between the experimental and control group was significant, because my p was less than 0.01. Okay, so that's meaningful. I've got some good news there, and that somehow my experimental group did better than my control group. But if I give this sentence in number 2, I think it gives a little bit more information. So I say that the 1-year survival rate increased by 20% in the experimental group, and I'm 95% sure that the real increase could be between 14% and 24%. My best guess is that it's 20, but it could be as low as 14, or it could be as high as 24. And so I think you'll agree that I think the second sentence gives you more information, because it tells you about the effect size and it tells you about the range. And so I'm trying to make the point here that confidence intervals are important to report, not just the p-values. So what this means is, when you say you have a 95% confidence interval, is that if you did the study over and over again, you replicated it, 95% of those replications, the true value of the population parameter would be within the interval. Okay, so you give your best guess of what that is, but you say it could be as low as this, it could be as high as that. So you can use this for means, for percents, for relative risk ratios. And to calculate it, now SPSS, if you ask it, will give you this information, but it's always your effect size plus or minus a critical value times the standard error. And for a 95% confidence interval, the critical value is 1.96, and this has to do with the normal shape distribution, and that 95% of the area in a normal distribution is within 1.96 standard deviations of the mean. So you have +1 standard deviation, -1 from the mean, and that's going to cover 95% of your people. So if you have a narrow confidence interval, that's actually a good thing, because you don't have a lot of variability. And the larger the sample size, the more likely you are to get a narrow confidence interval. So it's more informative. You don't have such wild guessing going on. If you have a wide confidence interval, you've got a lot of variability, and that happens a lot with resident projects because you may have a small sample, because you only have much time to run your studies as a resident, and so you might not meet the power that you want. You might not have the power. Your power analysis might have said to have 250 patients. Maybe at the end you only have 200, and so you didn't quite meet power, so you might have a lot of variability in a wide confidence interval. So what this is important too is if you have a non-significant finding, but you have a narrow confidence interval, you say, well, you know what? That shows that probably no real effect exists, because my confidence interval is so narrow. I've honed in on it, and even though I didn't reach significance, that tells me it's probably not out there to be reached. A wide confidence interval, maybe it didn't have enough patients. Like I said, for a lot of resident studies, that's the case. So just a couple examples here, and the last speaker will talk more about relative risk. But let's say you run a study and you find that smokers had an increased risk of bladder cancer, a relative risk of 1.9, almost double the risk. And the confidence interval could be as low as 1.3 or as high as 2.8. If that included the null value, which would be a relative risk of 1.0, then the p-value would be non-significant. And let's look at amoxicillin and a urinary tract infection, asking the question, is a single dose of amoxicillin more effective than 2 weeks of therapy for treatment of a UTI? Let's say that a single dose gives you a 61% cure rate, 2 weeks gives you a 74% cure rate. You find this just misses significance at p is 0.07, because your confidence interval, look how wide that is. It's -1.5 to 27.5. It includes the null value of 1.0, so not surprisingly, your p-value is non-significant. Okay, So the last speaker will talk more about relative risk ratio. So I just wanted to give you a sample of that. She's not talking about confidence intervals, so I wanted to throw that in as well. So I'm going to conclude my portion of the talk now and bring up Dave Sengstock, who will be introducing our Interactive Journal Club session. What was that? Okay. You just turn it on. You want to just take mine? That makes it easy. Give us a second here while we... All right. Okay.
Where do I plug mine? Can I take this out?
Don't know. A technician here? I don't have mine. They had loaded it up already. So I don't know if it's, where it's at. Okay, good. Might want to just give yourself a quick introduction.
All right. I'm Dr. Sengstock. I am the Director of Medical Education for 3 of the Beaumont hospitals. And my background is, in addition to being a geriatrician, I got a master's degree in statistics. I want to start by saying, guys, look, stop worrying about the stats. The issue that we really need to get across is how to design a good study. So what we've done here is set up an interactive journal club. I want you to focus on the one thing you never focus on, which is on the methods section. In fact, as far as I'm concerned, you can not bother reading any of the results. This is a study done at Beth Deaconess Hospital by a trainee, by a fellow in critical care medicine, and he was very interested in residents and evaluations. So what we're going to do is break up into groups, and the purpose of the exercise is to review this published study to help you gain experience in writing your own protocol. One of the things that I see most commonly is that residents have a lot of challenges in writing a protocol. And so what we'll do is we'll break up in groups, you'll pick out the variables, and I'm just going to tell you one of the main secrets of research. All research studies generally come down to 2 variables, an independent and a dependent variable. And indeed, when you plan your own studies, that's what it's going to come down to. So focus on design, methods, and how they plan to analyze the data. Talk about this in your small groups. I've handed study guides to the group leaders. And actually, if I can get the group leaders to come down for a second, I've got an answer key that I set up last night. I think they're fairly straightforward questions, but I do have an answer key. And then we'll reconvene at about half an hour later, and you can ask any question you want. Everything's fair game, and actually Karen will come up and if you have questions about stats. So we're going to break now. You have a number on your clipboards, so go to that part of the room. My number 1 people are here. Where are number 1? There's no 1. There's no 1. Oh, there it is in the center. So the 1 people are back there. You can just follow the numbers. And so, as I said, break up.
Do you want to bring them up to discuss or just have them ask questions, or what do you think?
What I did was I took my answer key and broke it into sections.
Okay.
I took them through that.
Okay.
But really what I care about is when people ask questions.
Yeah.
I'm not sure how to get them.
I know. It's hard. It's like going to
What's kind of interesting
Oh, okay, okay.
If I say something, it'll go out to the, are we going out to the remote? Are we going out to the remote site? Are connecting by simulcast. We're going to start up again in just a few minutes.
Forgetting to do that because you don't see these people.
Yeah. Most of the groups that were supposed to leave didn't want to leave, and they stood that late. There's about 120 that are supposedly here, but the 220 includes those simultaneous. Okay.
Dave, I have an envelope for you. I don't want to forget to give this to you. This is a token of our
Really don't have to do that. I tell you that every year. So I don't think I'm going to change your practice, but you still don't have to do that. All right. How do we know when everybody's back?
I think you should just wait and start.
Okay. If you want to come up. Sure. Is that thing working? Is your knee bothering you? Is your knee bothering you?
A little bit, yes.
I can tell.
After I sit for a while. Okay.
All right, I think, is this working? I think we're going to get regrouped, restarted, if we can quiet it down. Group. All right, so
Testing, testing.
is this working?
I don't think so. Can you hear me? Testing?
So the next lecture is going to be about some basic stats. But again, the main thing that you need to do for your projects is to set up a protocol. And the statistician can figure out stats, but you've got to write a good protocol or else it is garbage in, garbage out. And so I'm happy to go through the basic questions that you guys discussed. But if you have specific questions that's perhaps even more useful, I'm happy to entertain them. Anybody have questions either about the specific article or something that you're planning on doing in your own research studies? Don't everybody talk at once. Look, I'm not evaluating you. You're not. Go ahead.
So I wanted to do like a survey because there's like no standard like protocols for like post-op. People are doing or what they're prescribing. So what would be kind of the independent dependent variables on that?
Well, it's a survey, and so essentially we call that a descriptive study. So 10% of people said this, 20% of people said that. The independent would be your, whatever the subgroup. You want to break it down by surgical patients, women said this, etc. Those would be your groups, and your y-axis would be the percentage in a particular group. And that's fine. If nobody's ever done that, if nobody's characterized a population, a descriptive study is not bad. I would encourage you to try, again, if it's not been done, great, to try to think about groups to compare. So if you think that one group does something more than another group, now you actually have a comparison study, which is always a lot more compelling than just a 50% in this group said this, 40% in that group said that. To compare the groups, this is more prevalent in, I don't know, wealthy suburbanites in the inner city. That gets compelling because then you can think about your next study, which is an intervention study. But the y-axis would be percentage, the x-axis would be your group.
I would also encourage you to, I know you said there was nothing that was done in this area, but maybe there's a similar survey done in a different population. So rather than, coming up with your own survey, if you can look out there and see if there's something out there that's been validated, deemed to be reliable, that would be a benefit as well.
I'm going to double underline what you just said. It is always better not to build your own survey instrument. Take something someone else has done and validate it and use it. You can add a couple questions to it if you need to, but start with something that's been validated in other populations if you're going to do a survey study. What else? What time do we have?
152.
Okay. Well, so what was the independent variable in this study? Somebody can scream it out. I know we went through it, so.
All right.
Okay, and the dependent variable? Yep. And so essentially they didn't specifically state a hypothesis, you could infer one, but their specific aim was to assess the relationship between fourth-year course load and success during internship. But this here, relationship fourth-year course load, they defined it as the number of clinically intensive sub-I ICU surgical. So this is the way they define this variable. This is the way they defined their dependent variable, success during internship. Okay.
And I was telling my group that in your protocols, it's always good to have a hypothesis. Okay, maybe if you're just doing a descriptive study, you're not really testing groups, then maybe you wouldn't, and you would just have an aim or research question. But it's always good to have a hypothesis to test that you're comparing one group to another. Okay, so here they were comparing those who took more intensive courses to those who didn't, and then to see the effect on their first year as a resident.
So in a descriptive study that one gentleman discussed, there's really not a hypothesis to say. But if you push a little further and you think one group is going to be different than another group, now you got a hypothesis.
And that just makes it a stronger design when you can do that. Yes?
Could you comment on why you think they categorize outcome variable into X4?
You can do it either way. So that actually, let me just repeat the question. Why did they categorize it as excellent or poor? And by the way, there was one number that was in the middle. Did you notice that? 8 and 9 was excellent. 6 and under was poor. They never told you what they did with 7. So it's something in the middle. Why did they do that? Well, let me answer your question the way I'm not supposed to do it with a question. Why do we categorize 140 millimeters of mercury as hypertension? Why do we do that? 139, what's the difference between 139 and 140? I mean, not much. We, in human beings, like to see categories. Good, middle, bad. So it just makes it something that we can grab hold of. Great evaluation is associated with harder work during medical school. So we tend to categorize things for that reason. And I was actually telling my group, by the way, how many of you know anything about the HCAP scores? You've heard about these. Have you heard, the reason I'm bringing this up, I've heard people complain about it all the time. You know, they tell you that the only thing that counts is top box. The top box on the HCAP score is the only thing you get, that's the highest rating. If you get anything below the highest rating, that you fail. It's because so many people give their doctor their highest rating. That if they include the second to top box, all doctors would be perfect. Same thing in this. You guys know this. Every resident is above average. You know this because if you actually look at evaluations across your residency, 5 is not the average. The average is much higher than that. And so what they did was they knew that most residents get somewhere 7, 8, 9s as their evaluations. So they just took the top 2 and they said that's excellent. They took that next number down, 7 is middle, and everything 6 and below is poor. We like to categorize things, and there is a tendency for a higher score, but you could use it as a continuous variable. We just generally don't. Is that a reasonable answer? People like to categorize things.
Yeah, you categorize things, but it's not actually arbitrary.
It's always arbitrary, absolutely. Yes, you absolutely can do that.
I think the temptation for some people here would be to calculate an average score, but technically the data here are measured on an ordinal scale, okay, from a 1 to a 9. And so to take an average, a statistical purist would say, no, you can't do that. So they put it in, so they had 9 categories, so now they have 2 categories. They have poor and they have excellent, so the data are easier to work with. And they got a number in the middle that who knows what they did with. I assume they just threw out those people and didn't look at them in the analysis. It would have been nice if they would have told us that in the paper. So even though this paper was published, it wasn't a perfect study. We can still pick it apart and find some flaws.
There's lots of problems with this paper. All right, so it's a retrospective cohort. By the way, so these are internal medicine residents and Beth Israel Deaconess Medical Center who finished 1 year postgraduate training. So the conclusion of the paper was that there is a small but real effect of intense 4th year coursework on evaluation. And my question to you all is the internal residency class at Beth Israel Deacon Medical Center like your classes? I mean, this is Harvard. I mean, I didn't go to Harvard either. Is it the same class that you have? I don't know. I think it's a stretch to say that this is representative of most residencies across the country. Again, they have a higher proportion of AOA. They have higher board scores coming in. They have residents with PhDs coming into their first year residency. We have some of these in our residencies, but I'm not sure I think it's necessarily representative of most programs. A couple other things. I talked to my group about this, but as a general rule, you need to define, okay, so once you get your independent and dependent variables, you have to define your scales ahead of time. So if you're going to keep things as a continuous variable, that's fine. If you're going to categorize them as excellent and poor, you got to do this before you get your data, or else it's essentially academically cheating. You're going to fit your data to your hypothesis. It's cheating. Ceiling effect we just talked about, so same thing as HCAP scores. Most residents have very high scores. There's very little way to differentiate an outstanding resident with a 9 from a really good resident with a 9. That's what a ceiling effect is. So that's why they only gave those last 2 numbers excellent, and they didn't give the half of the scale because the scores just tend to be high. Let's see here. The next set, could you wait and see the data to set your criteria for excellent scores? We just talked about that. That's academic cheating. And last thing, I talked about this in my group. What's a covariate? This is very important. A covariate is a variable that you think can affect the outcome of your study that you have to adjust for in some way. So, again, the hypothesis of this study is hard work during your 4th year is likely to lead to better evaluations during your 1st year of residency. That's their hypothesis. if half of your class are AOA, you could see a scenario where these really high-performing medical students could not bother doing anything during their fourth year and still get really good evaluations during their first year of residency. They're just really high-performing residents. And so you need to find a way to adjust for that covariate called AOA status or high-class rank or USMLE scores. These are markers of a different group of people that may not need to do intensive fourth-year work to get a good evaluation. They may have sort of figured out how to get a good evaluation. These are what's called covariates. Again, I don't really care if you buy their hypothesis, but the point is you need to figure out in your study what the covariates are, measure them, and then adjust for them in the hypothesis. And here's just a way of thinking about it. I talked about this with my group. If you look just in your AOA residents and see if those among the AOA residents that worked really hard in their fourth year got better evaluations, and then look just in your non-AOA residents if they, when they worked hard in their fourth year, got better evaluations. That's adjusting for their AOA status. Now, statistically, we do it a little bit differently. We don't split them apart, but that's a great way to think about. So whenever you, look, about 6 months ago, I went to a conference from a researcher who was talking about resident wellness. Almost every paragraph started out the same way. After adjusting for age and sex and race and academic status, this variable was associated with that. That is adjusting for covariates. And so essentially it's the same thing we're talking about here. Look at your AOA group and see if the ones that work hard in their fourth year got better evaluations. Look at your non-AOA group. If you're looking to adjust for age, look in your old people. I'm a geriatrician. Look in your old people and see among your old people if the two variables are associated. Look in the young people and see if the two variables are associated. That's essentially what's happening when we say adjusting for a covariate. Now, like I said, statistically we do it a little bit different, but that's a logical way to think about it. Any other thoughts?
Very good. I mean, statistically, what we would do is a multivariate analysis. So when you meet with your statistician, you're going to go through all your univariate analysis, one variable at a time. But then if you ask for a multivariate analysis, that's when it gets more fun. You pit the variables against each other. You can control for variables and see if your main effect still remains, even when you control for age or, for example, AOA status in this example.
Right. And I'm done. And please fill out this is the first year we did this in quite this format. Let me know if there are things you want me to do next year. And I appreciated being here.
All right. Thanks, Dave. I'm going to switch back to my slides. Okay, very good. Okay, we're not going to take a break. We're going to go right into my talk, so please remain seated. You can, maybe if you just want to stand up for a minute and stretch if you want to while we're switching slides, that's good. Okay, very good. Thanks, Dave. Thanks for participating. Thanks for inviting me. Okay. Okay. Does he have his clip-on, Dave? Thanks, Josh. Did he take it? Took it off. Where's it? Is it that one? Okay, I'm going to use that one rather than this one. Okay, so what I want to do now is to delve a little bit deeper, like I promised in my first talk, into statistical tests. And I'm really going to keep it simple. If you looked at that paper we just reviewed, they use some really fancy things like generalized hierarchical modeling and all of this. Most residents, I'm here to say, don't use those kinds of statistics. So don't be intimidated by that. Those are kind of offshoots from some of these main statistical methods I'm going to show today. So I'm just going to keep it to the types of tests that you are most likely to use as a resident. And Like I said earlier, you've probably heard of these before, but you're probably not familiar with how to use them, or you've kind of lost that information over time. And so when you actually run your study, you'll get very familiar with that. I also, I think it's online, there's a thumbnail sketch that looks like this. It's like a grid, and it kind of tells you when to use a particular test, when it's misused, so you can kind of identify this. So I hope that's helpful as well. Okay, so let me get right into it then. So earlier I talked about descriptive statistics, just describing your sample, and that's like your table 1 in your protocol or in your results. Now we're going to talk about inferential statistics, which is really your hypothesis testing, where you get a p-value, where you get confidence intervals. And you're going to take your sample and you want to generalize to a larger population. So really the goal of your study is not to say what your patients are doing at your institution. Maybe you're looking at diabetics, but you want to look at diabetics in general. I guess the paper that we just read, maybe their goal is not to talk about these kids that came from Harvard, but maybe all residents. And maybe they weren't successful in that because they had such a high, population of, the AOA status and all of this. So the goal here is to generalize to a larger population to have good, what's called external validity. And you can use non-parametric tests. Again, if you have nominal and ordinal variables, and all of you will in your studies, then you want to use non-parametric tests because you don't make any assumptions about the data. You don't have to worry so much about whether the data are normally distributed and so forth. And parametric tests are used for analyzing continuous variables that are measured on a ratio scale, the real numbers that you can add, subtract, multiply, and divide. You do have assumptions about these data, though. You have to worry about whether the data are normally distributed. So if you think about my early example about the salaries, you have one group of employees, that have average incomes, and then you have another group and you throw Bill Gates in. You don't have then a normal distribution. You've got a skewed distribution. You don't have what's called homogeneity of variance. You have just variance all over the place when you throw Bill Gates in. And you want to make sure you have independent observations. So if you have two groups of people, a particular patient is in one group or the other, that they're not measured twice. So the question is, which test do I use? I just gave a talk last week, and one of the faculty members raised his hand, and he said, Karen, he says, that's really what we want to hear. Which test do you use? That's the most important question we have, and residents really struggle with this. So your first step in answering this question is to know your scale of measurement. That's why I spent some time earlier talking about the 4 scales of measurement. And it's also to know your goal. Are you comparing groups? How many groups do you have? Or are you measuring a relationship or an association between variables? Because your answers to these questions will direct you into one type of test versus another. So here are the key statistics that I'll be speaking about today. I'm going to be talking about chi-square, and there's a subset of that called Fisher's exact test that you use in certain circumstances. This is a non-parametric statistic, and it measures an association or relationship. Not a correlation. A lot of people will say correlation. It's not quite the right term. It's actually an association or a relationship. A t-test, you're going to be asking the question, are these groups different? And so it's a parametric test, and you're comparing these groups. Analysis of variance, you're also going to be comparing groups. I'll tell you what the difference is, though, between the t-test and an ANOVA a little bit later. And then we have correlation and regression. Now here, these are parametric measures, and you're measuring an association or relationship. But with parametric data, with the chi-square, it was with non-parametric. Okay, so it's probably not super duper clear right now, this chart, but I think as I go through these, you'll understand, why you would use one in one case and another in another case. If you have questions, again, please feel free to raise your hand at any time, and I will be happy to answer your question. Okay, so let's say I have a hypothesis that there's some kind of relationship between smoking and socioeconomic status. I may think that people that smoke, maybe they're, have a lot of stress because they don't make a lot of money, they're working a couple of jobs, and so they're smoking maybe to alleviate some of that stress. And so maybe that's my hypothesis here. And so I look at 105 people. This is actually cut out from an SPSS output. And there's 6 cells because we have socioeconomic status categorized as low, middle, and high. And of course, I would operationally define what the income would be for each one of those categories. And then I have my smokers, which are 26 people, and my non-smokers, which are 79. So I lay it out here in what's called a contingency table. And it's a 2x3 or 6-cell contingency table. The first number in each cell, for example, the upper left there is the low socioeconomic status and the smokers. And I have 7 of those. So the first number in each of those 6 cells is the actual number of people that fall in there, how my 105 people are divided. And so then I have 13 in the middle socioeconomic status group that smoke, 6 in the high. So what I've circled there are the percent within the socioeconomic status. So 38.9% of the low group smoke, 20.3% of the middle group, and 26.1% of the high group. So these are my rates of smoking for the 3 socioeconomic status groups in my study. So the question is now, do I have support for my hypothesis that there's some kind of association between these categorical variables? So it kind of looks that way because I was thinking that the low socioeconomic group might be more stressed, as I said, and smoke more. So they do have the highest rate of smoking in my study at 38.9, but I can't just eyeball the data. I really have to run a statistical test. And that's the ideal thing to do. And so in this case, I would run a chi-square because, again, I'm looking at an association between categorical variables. So this is a bread and butter test. I have run many, many of these tests, and I can guarantee you in your study, you will be running a chi-square test. And you'll be running several of them. So it's really important to understand it, and it's pretty simple. So it's very common, looking at an association between categorical variables, and you're looking at what are called the observed and the expected proportions. So you would expect if it was no effect of socioeconomic status, an equal number of smokers within the 3 groups. And then you get something else. You get what you observe, which is a little different from that. And so we're trying to answer the question, is it different enough for it to be statistically significant? Or is it just a chance fluctuation? And you got to make sure you have enough people in each cell. If you have 5 or less in each cell, then it's not a great test to run because you don't have enough cases. And so I'll talk more about that in a minute. So I actually ran this test on the data, and I circled the p-value. This is actual output from SPSS. This is what it looks like. The only line that you need to worry about is the first line, which is Pearson chi-square, and it says 2-sided p-value, so you're looking at both ends of the curve. They could have increased their smoking or decreased their smoking, depending as we move through the categories. And my p-value is 0.268. So you probably know enough about p-values to know if that's something to get excited about. So do I have support for my hypothesis? Somebody tell me, is that significant? No. Remember, it's usually 0.05 is the line in the sand. You can make it 0.01, some people do, but it's typically 0.05, so we'll just keep with that. So it's non-significant. And so there's no association. So even though it looked like my low group was maybe smoking a little bit more at 38.9%, I have to conclude that there's no association here, and that was just a chance variation. It could have just, these numbers could have been scrambled differently, and it would have been the same. Okay? All right, good. So there's an alternative to chi-square, as I mentioned. There's a Fisher's exact test, and it's based on a statistician named for him, R.A. Fisher. And it's called the exact test because it's based on exact probabilities. But the main thing I want you to focus on here is that you use it in a special case, which is when you have a 2x2 contingency table. So in my table, I had a 3x2. I had 6 cells. You only use the Fishers when you have a 2x2. And SPSS only gives you this line in the output when there is a 2x2 table. And then you don't have to worry about how many people you have in each cell because it's based on exact probabilities. So having a low n is okay in this case. If you had a 3 by 2 and you had a low N, then you would have a problem. You'd have to not have 3 categories of socioeconomic status, but maybe 2. Divide them into 2 rather than 3. So there'd be other ways of dividing the data to actually get a p-value that way, or you could just report the descriptive statistics and not run a test. So here's an example of the Fisher's exact test. Yes, question? ANOVA? You wouldn't do ANOVA on that because ANOVA, in a minute, I'm going to discuss that. So that's a whole different ballgame. It's actually, the ANOVA is when you have an outcome that's continuous. So let's say instead of categorizing social economic status into 3 categories, let's say I actually collected their incomes. And let's say then I looked at smokers, or not, well, let's say maybe I had 3 groups. I'm just going to make 3 groups. So I have smokers that smoke at least a pack a day, smokers that smoke occasionally, and people that never smoke at all. And then I want to see, is there a difference between these 3 groups and their income? That is when I would do an ANOVA. Because I have 3 groups of people, that's my independent variable, and my dependent variable is their income rather than a category, low, middle, and high. I actually have a real number, and so I'm looking for the 3 groups then, is there a difference in their average salaries? So that would be analysis of variance. Mm-hmm. Yeah, that's your independent variable, is how you have your groups, yes. Yeah. Okay, any other questions? That's a good question. So yeah, you're going to hear more about ANOVA in a minute, but I kind of gave you a preview there when you would use it. Okay, so getting back to this now, this is the Fisher's exact test, and you use this when you have a 2 by 2. So I've got, again, I'm talking about categorical variables. In this case, I'm looking at lung cancer. So I want to look if there's different rates of lung cancer between my patients that smoke and those who don't smoke. Okay, and so I have 105 people. I've got my 26 smokers, my 79 non-smokers, and I have 4 cases of lung cancer in the study, 3 for the smokers and 1 for the non-smoker. So the percents that I've circled here is the rate of lung cancer within each of the smoking groups. So 11.5% of the smokers went on to develop lung cancer, only 1.3% of the non-smokers did. So that looks like a big difference, and indeed, when you run your statistics, in this case, I would report the Fisher's exact test, because that prints out. I mean, you could also report the Pearson's chi-square, the first line, but it's better to report the Fisher's exact test in this case, and the p-value is 0.046. So I have a significant finding here. So I can say then that there's an association in my study between smoking and cancer, and that the smokers were more likely to develop lung cancer than the non-smokers. Okay, I can't really say cause and effect. I didn't force people to smoke versus not smoke. So it's not a real cause and effect thing, but these things go hand in hand. It's an association between these 2 categorical variables. Okay, so this is used a lot too, because a lot of times you have 2 variables with 2 levels in each. You know, somebody's dead or alive, they got the treatment or they didn't. It's used a lot in medicine. So, so Fisher's exact test is a very common test to be used as well. Okay, so now I'm going to ask a different question. I'm going to ask, rather than if variables are associated, I'm going to ask if these groups differ. So I have my 26 smokers and I have my 79 non-smokers. Now my hypothesis is there any relationship, do the groups of smoking differ in terms of their BMI? So a lot of people will say, well, if I quit smoking, I'm going to gain weight. You may hear patients say that. So there's kind of this idea out here that there's something going on between smoking and weight gain. And so I want to look then for my 26 smokers, what their BMI is versus my 79 non-smokers. And I ask the question, do these groups differ? So I have 2 groups here, and here are their means. The mean BMI is just over 25 for the smokers and just over 26 for the non-smokers, and I have the standard deviations as well. So not a lot of variability there, so that's good. And so in this case, I'm going to look at what's called the unpaired t-test, It's also called a student's t-test, and it's named after William Gossett. And there's a little story here that William Gossett, he was in Ireland, and he was a worker at the Guinness brewery, and he was telling trade secrets, and so he would hide his information and call himself student, so that he wasn't giving away any trade secrets from his company. So that's the strange story. It has to do with beer as to why we call this the student's t-test. You may call it the unpaired t-test or the t-test for independent groups. It actually has 3 different names. And a very common test. You use this when you have 2 independent groups. Now, if you have 3, you're going to use ANOVA, but so it's only when you have 2 that you use the t-test. And you're testing for a difference between these groups. So you see the 2 means there for the BMI, and the question is this some natural fluctuation in BMI, or is this a real difference between the smokers and non-smokers? And my outcome, my dependent variable, should be a real number on a continuous scale. And again, I have those same assumptions for any parametric test, that the data are normally distributed, that there's homogeneity of variance, and that the observations are independent. So I either have smokers or non-smokers, so you're in one group or the other. So this is a clip here from SPSS, and I'm testing for a difference then between these 2 BMI groups, the smokers and the non-smokers. So I have circled the p-value, and it is 0.4. So no difference. So there goes my hypothesis, all right? Hopefully it's interesting information anyway, but I don't have any support for the idea that, the people that are smoking are somehow thinner, and then when they quit smoking, they're going to gain weight. So there's no evidence for that in this study. These 2 BMIs could have been just as well been reversed. It's just a natural fluctuation. That's what I have to conclude from my p-value here of 0.4. Any questions on that? So you just got to know, what number to circle here. I mean, you might get confused. There's another significance value here under Levine's test. That's actually testing for the assumption that there's homogeneity of variance, and so here it's non-significant. So I read the line of the table, equal variance is assumed, and so I circled the top p-value of 0.4. But that's kind of a fine point, and your statistician will hopefully help you through that and tell you where the p-value is in this table here. So the story here is that I have no difference between these groups. Okay, questions? Okay. So all of you will be running t-tests. It's so common to do that. Now there's another type of t-test. It's not an independent or a student's t-test, or it's for a within subjects design. It's called a paired t-test. Let's say I have a design where I have an intervention, and I'm trying to help these people quit smoking. And so in my study, I have as a variable here number of cigarettes with an underscore B for before my intervention. So they were smoking almost a pack a day at 19.6 cigarettes on average, my 26 smokers. And then I do some kind of intervention, some kind of behavioral modification program that they, learn about how to cope with their stress and not reach for a cigarette, or maybe I show them a video about all the ill effects of smoking, whatever it is. And then I measure, a couple weeks later to see if they're smoking less. And lo and behold, I find that afterwards, the average is this like about a pack a day at 11 cigarettes. And so that looks good. It goes almost like from a pack a day to a half a pack. It would have been nice to have it even lower, but this is the real world, and I'm not going to get a change overnight. So my question is, did my intervention make a difference? So I'm going to use a paired t-test in this case, because in this case, I have a within subjects design. I have a pre-test and a post-test. So it's the same 26 smokers, but they're measured twice. They're measured before my intervention and after my intervention. So that's my 2 groups, but my observations are not independent, they're dependent because of the same people. And these designs are nice because you don't have to worry about a bias. You don't maybe have to worry about age affecting this, because each person serves as his or her own control. So every factor within that person is replicated for the after part, and so it carries over. So it's a great design to use in terms of eliminating bias between your groups. So I'd use what's called a pair T test. My observations are dependent here. It's a within subjects design, pre-post. I have pairs of observations, and I set up pairs in the database. I see where I calculate a difference score. So if it was 20 cigarettes before and now it's 10, my difference score is 20 minus 10 is 10. And then I want to be, if there's no effect, my mean difference is 0. If there's some kind of change, that means it's not 0. And I hope that my distribution of how many cigarettes they smoke is normally distributed in both phases of the study. So here I get my output in SPSS. So I ask for a pair T test. And again, we're looking at 19.62 cigarettes before, 11.3 afterwards. And so the difference between that is an average of 8.30. And way to the right, I get my p-value, which is 0.016. So am I happy as a researcher? Have I made a difference? Yes, right? Because my p-value is significant. So I say, great. I worked on this study. I put people through this intervention. I collected informed consent that they consented to be in the study, and they had an intervention, and I went through all this trouble to do the study, and I actually did make a difference. It would have been nice if all of them had quit smoking, but they cut their smoking about 50%, and it was statistically significant. So this is something that I can present and be happy about. Okay, so now I'm going to get into ANOVA, and I'm going to now look at my groups in 3 groups rather than just looking at smokers and non-smokers. What if I say I have non-smokers, and then I have light smokers, and I have heavy smokers? Okay, so I take my 105 people, and I've got 79 non-smokers, 17 light smokers, and 9 heavy smokers. And now I'm going back to the hypothesis of BMI. I'm wondering if there's any differences in their BMI. It looks like my heavy smokers have the lowest BMI at 23. So is that significant? Looks like the non-smokers and the light smokers are very similar, just looking at their means there, the descriptive statistics. And of course, I operationally define what I mean by light smoker and heavy smoker. So I say light smoker is less than a pack of cigarettes a day, and a heavy smoker is at least a pack a day. So I always got to remember to define my independent variable here. And so I'm going to run, for this case, what's called an analysis of variance, or ANOVA. It's also called an F test. Again, it's named after that guy Fisher that I told you about. He's got his name on this test, too. Well, I have 3 or more groups. Remember, if I have 2, it's a T test. So now 3 or more is ANOVA. And I'm going to test for a difference between these groups. And the outcome is a real number. Okay, so here the outcome is BMI, real number. And again, I have the same assumptions because it's a parametric test. So I have to concern myself a little bit with those assumptions. Okay, so we'll get to the results here. So non-smokers BMI, light smokers, heavy smokers, just to refresh your memory here. So the heavy smoker kind of looked like maybe they had a lower BMI, so maybe there was something going on there. But I run my analysis of variance, and my p-value associated with the F test here is 0.310. So I say, well, I guess it didn't really make a difference. So I have to conclude that there's no difference between these 3 groups in terms of their BMI. Now, I do remind you that I only had 9 smokers, heavy smokers. So I may not have the power to show this difference. Maybe this 23 really is lower than the 26, and if I'd had enough heavy smokers in my study, I may have been able to find that to be significant. So it was kind of bad for my design that I didn't have as many heavy smokers, but of course we don't really want to wish people to be heavy smokers. So, so there's what's good for the people versus what's good for research sometimes. So anyway, so no effects there. So I conclude that I have no support for my experimental hypothesis, and that I keep the null hypothesis, or I fail to reject the null hypothesis. Now, what if that F test would have been significant? What would I have done then? So let's give an example where it is. So you actually don't want to stop there. If the F test, if the ANOVA is overall significant, you want to conduct what are called post hoc t-tests. Okay, so this may say, you might say, well, what in the world is that? Well, post hoc means after the fact, and t-tests, you know, are two groups. So what I'm going to do then is take all possible comparisons, every pair I can look at and see if they're different. So I kind of want to see, I get an overall F statistic that's significant, and now the next question I'm going to ask is, well, which groups are different from each other? I mean, that's, I think, what you would ask if you looked at the data. You want to know where the differences lie. So that's what you do next. So you do multiple comparisons, and there's a whole bunch of these tests. I have no idea why there's so many. There's one that there are, and so, you know, you don't want to check every box. It's easy in SPSS to click on every one of these tests. But I generally run the Scheffé test because it's a little bit more conservative. So it'll pass the Scheffé test. It'll pass the other ones. But, you know, if you have a preference, there's some people that'll vote for one versus another. And they vary in terms of their likelihood of making a type 1 error. That's what I mean by conservative. So the Scheffé test is most conservative. In other words, you're not going to jump the gun and say something significant. Type 1 error is less likely. The Duncan is the most liberal. You're likely to make a type 1 error and jump the gun. And Newman-Cool's is kind of in the middle. Okay, that's just the general rule of thumb on these tests. Okay, so I have 3 treatments because I'm running ANOVA. And these are the number of cigarettes smoked per day after these 3 treatments. And these are the means. So it looks like treatment B is the one to vote for here because after treatment B, whatever treatment B was, I have less smoking than I do in treatment A and treatment C. So when I run an analysis of variance, lo and behold, I get a significant p-value. P is less than 0.001. So I say, okay, that's exciting. There's an effect here. But then I want to know where the difference is. Well, I think eyeballing the data, you can kind of maybe see where the difference is. But if you have 6 groups, and, you know, it might get a little bit more complicated. So you want to look at each possible pair. But I'm going to make it simple here in that we only have the 3 groups, so we don't have so many pairs to look at. So you want to know which groups are different from each other. So I'm going to run the Tukey's post hoc t-test here, each one. So I'm going to look at A versus B, A versus C, and B versus C. So that's every possible combination. And so, again, B is my lowest. So A is different from D, and also B is different from C. But A versus C are not different, okay, the 2 that are just over 27. So it is the fact that treatment B is the one that's the winner here. Okay, it's better than treatment A, and it's better than treatment C. You understand that? See how I looked at all possible comparisons and get a p-value for each one? Okay, because it isn't just good enough to say I've got a significant ANOVA here. Where's the difference? So that's why you get, and you can get pretty long tables looking at every possible pairwise comparison, so it can get complicated. So there's some variations of ANOVA that I want to go through just in case you see these terms. There's what's called a one-way ANOVA. And that just means you have one independent variable and one dependent variable, so it's a very simple design. And then you can have a two-way ANOVA that you have 2 independent variables and 1 dependent variable. And what's cool about that is you can look for what's called main effects of each variable, or you can see how the 2 independent variables interact with each other. So you can look at main effects and you can look at interaction terms. So it's a little bit more complicated. It's called a factorial design. And there's also something called repeated measures ANOVA. So maybe you're looking at systolic blood pressure on day 1 and on day 2 and on day 3 between 3 different groups. And so repeated measures, you're looking at them again and again. So that's a within subjects design. And then multiple analysis of variance, or MANOVA, it's the same as ANOVA, except there's multiple dependent variables. Okay, so you can have multiple dependent variables as well. So don't be too confused about these terms. Just kind of know that they're all looking at the same thing, that you have 3 or more groups, and that your dependent variable is continuous, and you may have more than 1 dependent, and you may have more than 1 independent as these designs get more complex. Okay. Okay, any questions so far? Okay, looks like you're hanging in there good. So, okay, I know statistics probably isn't the most exciting topic, but I'm just trying to really make it relevant to medicine here for you and kind of just hone in on what you might be using as a resident. So, okay. So my question here is there a relationship between these variables? So I collect two pieces of information in my study, probably collect more, but just for a simple case here. I have the number of cigarettes and the BMI. So every day there's a pair of numbers here for each person. So the first person smoked one cigarette and their BMI was 30.1 and then so forth. Until I get somebody that's smoking 100 cigarettes and their BMI is 19.9. So in this case, I'm actually just looking at, I've got two continuous numbers here, right? I've got two real numbers, number of cigarettes smoked and BMI. I didn't put BMI into categories of normal, overweight, obese. I'm just actually putting in their actual number for the BMI. And I say, is there a relationship between these two? I might say, is there a correlation between these two? This is when you can use the term correlation. So the test that I would use for that is called Pearson's correlation, named after Carl Pearson. And you look at the degree of relationship between two variables, and these variables are normally distributed. They are, the relationship is a linear relationship. So as x increases, y increases. So if I have a curvilinear relationship, I don't want to run this test. Both variables are measured on a ratio scale. They're real numbers, and they're measured on the same subjects. So each subject, I collected BMI and number of cigarettes. And when I draw these out in what's called a scatter plot, here are three examples of it. So the R value that I get when I run this is a continuum. It runs from negative 1.0 to positive 1.0. And an R value of 0 would be no correlation. We call a positive 1.0 is a perfect positive correlation. So if you look at the first graph there on the left, that's a perfect positive correlation. So as x increases, y increases. And if I plot that out, all the points would fall on a straight line. Well, of course, this really never happens in the real world, but you want to be as close to this as you can, or you want to be as close to a R of negative 1.0 as you can. So both ends of the scale are the best to be at, either a negative 1.0 or a positive 1.0. So a negative correlation, this is a perfect negative correlation, so as x increases, y decreases, and it does it perfectly. There's no scatter around that line. And then the third example on the right is no correlation, an R of 0. So I can't draw a line at all. So what you want as a researcher to get a correlation, you want something as close to a positive 1.0 or as close to a negative 1.0. So you want to be away from 0. So in my study, again, my simple study here, just looking at number of cigarettes smoked and BMI, the Pearson correlation value that I get is a negative 0.169. Now, is that a strong negative correlation? Remember what I said. Let me just go back. I want to be as close as possible to a negative 1.0 or a positive 1.0. So I have negative 0.1. Now, that's pretty close to 0, isn't it? Yeah, so it's really nothing to get too excited about. And indeed, the significance associated with that is 0.410. And so that's non-significant. So my hunch is right that it's really not much of a relationship. And when I graph it, which you should always do, you can see all the scatter around that line. It's going in a negative direction, but there's so much scatter there. So I don't have a lot of good predictability. So knowing how many cigarettes somebody smokes doesn't really predict what their BMI is going to be very well. Okay, so that's just a simple thing between two continuous variables. What if I have a more complex study where I'm looking at multiple variables? So I have an outcome where at the end of my study, people either quit smoking or they're still smoking. And the variables, I look at a whole bunch of things, but I include number of cigarettes that they're smoking, the BMI, their socioeconomic status as a categorical variable, gender as a categorical variable. And so I'm asking the question here in a more complex model, which variables predict the outcome? So my outcome is binary, right? It's either quit or smoke. And that's very common in medicine. Somebody's either dead or alive. Somebody either has a disease or they don't have a disease. So this type of model is very common. So I'm going to be looking here, rather than a correlation, at a regression analysis. And I'm trying to come up with an equation to predict the outcome based on one or more input variables. The assumptions is that I have a linear association between my variables, again, that they're normally distributed and they're measured on the same subjects. And so there's variations on regression. The one that I do the most and for residents is the logistic regression. Really not linear, but linear is a single outcome or dependent variable, a single independent variable, and both variables are continuous. Multiple regression is you have a single continuous outcome and several independent variables. And here's the one that's used the most, logistic regression in medicine here, because it's the outcome that's binary, disease or no disease, dead or alive, smoking or not smoking. And then you can have several independent variables like I did in my model here. I'm looking at socioeconomic status, I'm looking at gender, I'm looking at the number of cigarettes smoked. All of those may predict my outcome of whether they continue to smoke or not after my study. So let's make a prediction. So in this, I run the model. I throw in all these variables. I tell the SPSS that my dependent variable is continuous, and it's, categorical, and it's whether they smoke or they don't. And I throw in all these variables. Now, before I throw in the variables, the computer 61.5% of the time is going to predict that they still smoke, okay, because that is what I have. Most of the people are still smoking, unfortunately, after my study that are non-smoking. So you'd be right 61.5% of the time if you say that somebody still smokes. If I throw in all my variables, then that number bumps up to 76.9%. So obviously knowing some of these variables helps my model. It helps my predictability here. It increased it from 61.5 to 76.9. And so here's how the output looks. The number of cigarettes smoked before my study was a significant variable here, and the p-value was 0.024, which is significant. The other variables I looked at BMI as a continuous variable, socioeconomic status in 3 categories, gender in 2 categories. You see how the significant column there, they're all greater than 0.05. So none of those mattered. So knowing the number of cigarettes somebody smoked before the study was the only variable that made a difference in predicting whether they were still smoking or not after my study. The other ones didn't matter at all. But this is great, though, because instead of looking at each variable individually, when I do a multivariate analysis, I'm looking at multiple variables simultaneously. So it's more powerful of a analysis to do. So that's why in your studies, when you meet with your statistician, you can look at univariate analyses, and then you can move on to a multivariate analysis, and that would be a great way of looking. And people are getting more savvy to this. I know over the years there's been more and more demand to look at multivariate analysis rather than just all the univariate analysis. Okay, questions so far? Okay. All right, let me just continue on here. I want to talk just a little bit about non-parametric tests. So what happens when you don't meet these assumptions of the parametric tests? What can you do? You may have a small sample size. Your dependent variable may be categorical. And so there are non-parametric tests. So if you have a case where normally you would have used a student's t-test or an unpaired t-test, there's a non-parametric equivalent. So if you have a real low N in your study, because maybe the disease you're looking at is quite rare, there aren't too many patients with that particular tumor, instead of doing a t-test, you might want to use a Mann-Whitney U-test. So if you see that term, don't be thrown. It's the same as a t-test, but it's just used for when you don't meet these assumptions. A paired t-test, the non-parametric equivalent is a Wilcoxon sign-ranked test. ANOVA, the equivalent is a Kruskal-Wallis test, and Pearson's correlation has a Spearman's rank correlation. So sometimes you might want to use the non-parametric equivalent if you have data that are skewed, if you have a low N. So hopefully your statistician will make this judgment and help you with this. But when you're reading the literature, if you see these terms, you can say, okay, I saw that before, I know what that means. It's really just the equivalent of the parametric test, which you hear more often. Okay, any questions? No questions? Okay, just the last part of my talk, I've got just a few more minutes here before we take a break, and then I hope I don't lose you all at the break. You stay with us for our last speaker, who is coming in from Merck, and is really going to talk a lot about, you hear about odds ratios. We had that in our paper, odds ratios, relative risk ratios. She's going to explain all that to you, so it's worth staying around. One part of her talk that wasn't in her talk that I want to talk about, just it kind of segues into hers. Rather than talk about parametric testing and statistical testing, I want to talk about diagnostic outcomes for a little bit here. So if you have a patient that's as a physician or as a patient, what does it mean to test positive or test negative? And so in some of your studies, you're going to just be calculating what's called sensitivity and specificity. You probably heard these terms before, but I want to make it clear that you understand where these terms come in. And I was just analyzing some data now that I'm calculating these things. I have an OB resident who's looking at whether he can predict who's going to deliver via cesarean delivery. And he has this, there was a paper published by a guy named Burke, and he came up with a nomogram. He said advanced maternal age and a larger the head circumference on the fetal ultrasound and some other factors. If you know those things, you can make a prediction as to whether somebody's going to have a cesarean delivery. So what we wanted to do then is to see whether that applied to the patients we see at our hospital, because they base this on patients that were European, and so we wanted if this was the same, and I'm finding that it's really not, that we don't have good sensitivity and specificity for this nomogram. So sensitivity is the probability of testing positive if the disease is surely present. So you want to have good sensitivity for a test. You also, on the flip side, want to have good specificity. So it's the probability of testing negative if the disease is truly absent. And then you want to worry about positive predictive value. That's the probability that a patient with a positive test has the disease. The flip of that is the probability that a patient with a negative disease, the negative test does not have the disease, so negative predictive value. So those are the four things that you report out. And it's very simple to calculate this. You're talking about a 2x2 table, and the gold standard, in this case, for the present an example, was cesarean delivery. What we know in the records whether they had a cesarean delivery or a vaginal delivery. And then we know, based on that nomogram, whether they were predicted to have a cesarean delivery or a vaginal delivery. So we can calculate these things. So you have A, B, C, and D in your 2x2 table here. And so you just simply calculate simple math here to get these four figures. So in this case here, I've got 16 people that screen positive and actually have the disease. And so then, when I calculate these row and column percents, you see my sensitivity is 59%, my positive predictive value is not so hot at 20%, and then my specificity is 67%, and negative predictive value is 92%. And so it's no mystery as to how you get these numbers, but you always have to have a 2x2. If you've got more categories than that, then you're not going to be concerned with these types of statistics. So you really want to have sensitivity and specificity to be high, but you can't always get that. And so you have to decide what's really important here. So if you lower how you call somebody positive, you lower the criterion of positivity, you're going to get more sensitive tests, but you're also going to lose specificity. If you raise the criterion, then you get increased specificity, but then you lose sensitivity. So an example, in JNC8, a normal blood pressure, diastolic blood pressure is less than 90 millimeters of mercury. If you lower the criterion to 85, you would pick up most hypertensives, but then you're going to be falsely labeling people as hypertensive that are really normal-tensive. If you raise it to 95, then you're going to have normal-tensives that test negative, but so would a greater proportion of those with hypertension. So you can kind of see the balancing act here. So you want to increase sensitivity when there's a big price to pay for missing a case. So if there's a serious disease and there's a treatment out there, like in the example of PKU, you know, you want to be able to get that. If the disease is dangerous and that it could spread, such as sexually transmitted diseases, or if the future testing is not really costly or risky, such as you can bring a patient in and have a number of blood pressure readings. You want to increase specificity if the cost and risk is high. So breast cancer, that further diagnostic testing is high. But then you have to say to the patients, well, a negative screen doesn't not necessarily mean that you're disease-free. So that's what you kind of, again, a balancing act between those two. And the last thing I want to do, 1 minute over, so just bear with me here for just 1 more minute. The interpretation of results. So the size of the p-value does not indicate the importance of the result. And I think the next speaker is going to also make that same point. So we've talked a lot about testing today and whether p was less than 0.05 and should you be excited. But sometimes you may see an effect and it may not have reached significance, but it's still something that's clinically significant. So you have to think in terms of a clinician and a statistician simultaneously. And you want to make sure that you do give an appropriate interpretation. So you want to talk about differences between groups, associations when it's appropriate. And remember, correlation does not imply causation. So sometimes, you know, studies are interpreted such way you kind of jump the gun and you get excited and say you have a cause and effect. Unless you really did a randomized controlled trial where you were manipulating something, you know, assigning people to smoke or not smoke, or in this paper we read today, assigning medical students to intensive courses versus not intensive courses, you know, then you could say perhaps that you have a cause and effect. But in the real world, you often can't do that. So you just say you have a correlation, a relationship, and it doesn't imply causation. And again, remember between the difference between clinical significance and statistical significance. You got to wear two hats here. One is a clinician, one is a statistician to really interpret your results fully. So allow plenty of time. I mentioned this at my first talk last month. All these things take time. It happens all the time. I had a resident just earlier this week, and she called me up and she said, I have an abstract that's, well, this was Monday. She contacted me late Monday, and she said, I have an abstract that's due Wednesday. And here's my Excel file. And so, oh my God, it was all a mess. You know, I couldn't tell one data point from another. I had to get on the phone. We had to go through it. I ran an analysis. It wasn't what she wanted. I had to redo it. I still don't think I got what she wanted, but there's no more time. The deadline was yesterday, so what I gave her, you know, by Tuesday night, that was it. She was just going to run with those stats. So don't be like that resident. That's no fun. You know, I didn't get happy when I got that phone call, and she's miserable because she's got to rush through this abstract. She doesn't have time now to, I really think I didn't give her the analysis she was looking for, you know, and I did the best I could, and she didn't explain things really clearly, and, you know, if we had more time, we wouldn't have had these problems. We could have met face-to-face. This was all done via email, over the phone, and it was all a big rush job just to try to get these numbers, you know, for her abstract. And so that's a lot of times that'll pull somebody into my office is when an abstract is due, but I'd much rather see you earlier on. So find this person in your institution to help you along the way early on with your power analysis, with writing your protocol, and helping you with the statistics, and do it early so that you've got time to really have the results gel in your mind and have time for subgroup analysis, and it won't be quite as hard that way. You'll make your life a lot easier and your statistician's life a lot easier too. Okay, so I think that's all of my slides. Oh, okay, I just like to end with this. This was, you hear this all the time. There are three kinds of lies: lies, damn lies, and statistics. And so this was actually popularized by Mark Twain. So don't lie with statistics. All right. Any questions? Yes. Yes. Right here? So what if we don't have a binary? Then you would be looking at the other ones, the linear regression or maybe a multiple regression. So logistic is only when you have a binary. Three independent variables? Yeah, I mean, oh, the categories. Yeah, you can have that. Yeah, you can, in these models, you specify in SPSS which variables are categorical and which ones are continuous. And so you can actually have a mixed model like that. It depends on if the outcome is binary, then it would be logistic. If the outcome is continuous, then it would either be multiple or it would be linear. So it just depends. But it's you don't have to worry so much about that. Your statistician will worry about that, and they'll tell you. But it's one variation or another of regression. Okay. Well, hopefully you do. Yeah. Okay. All right. Any other questions? All right. Thank you so much for your time. And we're going to take a break now. Let's come back in about maybe 7 minutes or so to hear our last speaker. So please don't leave. Please stick around to hear our last talk. Okay.